Hello friends and welcome at my channel. Today I would like to go through the following problem. I would like to sketch the graph of x cubed minus 3x squared, and we're gonna get through all the points that are needed in order to produce this graph correctly. So I call it normally lucky 7. So there are 7 steps that we're going to go through, and we start with the domain. So what are the values that we can substitute for x? And the answer is everything. So all the reals, we are now at real numbers. So the domain consists of all the real values, x from R. Okay, second point in our investigation is there any kind of symmetry involved here? And the answer is no symmetry is involved. Why not? Well, in order to fulfill this conditioning, if we're dealing with polynomials, we need to have only even powers, which is not the case. 3 is an odd number. In order to be symmetric considering the origin, we need to fulfill this conditioning, which is only fulfilled for the polynomials if we have only odd powers, which isn't the case here because 2 is an even number. So no, let's write simple symmetry. Okay, number 3. Well, we obtain the behavior of the function if we go with x values if we run towards plus or minus infinity. So let's see what's happening if x is running towards plus infinity for our f of x. Well, the dominant term expression is the expression with the highest power, which is x cubed. If x is getting very big and positive, x cubed is getting very big and positive as well. So plus infinity is the result here. And if we are talking about x going to minus infinity of f of x in this case, then x is getting huge values which are negative. If we cube it, it's still going to be negative, so we're going to minus infinity. All right, number 4. Well, these are the points of interception with the x's. What do we have? Well, let's put x cubed minus 3x squared equal to 0. We can take x squared out of the parentheses. We're going to have x minus 3 remaining equals to 0. And now we have a product which is equal to 0. So one of the factors must be equal to 0 as well. It's either x squared equals to 0, which leads to x1, 2 equal to 0, or x3 equals to 3. So we have a double 0 point and a single 0 point. There is a difference between those two. Hope you know. If you don't, double 0 point means that the first derivative here is also 0. Think of it, and maybe next time we'll prove it. Okay, so those are the intersections with the x-axis. So basically we have n1, 2 with 0, 0, and n3 with 3, 0. All right. The intersection point with the y-axis, well, since we go through the origin, it is the same point. So 5. First derivative, we're going to extreme values. 3x squared minus 6x. Let's put 3x squared minus 6x equals to 0. Well, I can divide it by 3. I would have x squared minus 2x equals to 0. And now I can take x out. This is x minus 2 equals to 0. So x1 is 0, x2 is 2. What did we mention? We mentioned that if there is a double 0 point, then maybe the first derivative is equal to 0 as well, which is true. So we produce a second derivative here, which is 6x minus 6. Well, let's see what will happen if we put the values we have into the second derivative. So f second prime of 0 is minus 6. It's less than 0. So after that, we go down in both directions, which means we have a max at 0, 0. And what is f second prime of 2? This is 6 times 2, which is 12, minus 6 is 6. It's positive. That means we go up in both directions afterwards, so it's a min. And we have 2, and what is the y value? Well, let's put it inside our function. Once again, that's our function that we're dealing with. And f of 2, in this case, would be 8 minus, I got 12, which is minus 4, okay? 2 and minus 4 is the min. Well, very important points for us. And number 6, this is the point of inflection. For these reasons, we need the second derivative, which was 6x minus 6. We put it equal to 0. We're gonna get 6x equals to 6. We divide it by 6. X is equal to 1. And, well, in order to be totally correct, we produce a third derivative as well. The third derivative at 1 is still 6, so it's unequal to 0, so we have point of inflection. Let's call it W, and we have it at 1, and let's produce f of 1, which is 1 cubed minus 3 times 1 squared, which is 1 minus 3, which is minus 2. Do we have enough? Yes, we do have enough. Let's produce the graph. 7, the graph. So what do we know? We have a double 0 point at 0 and a single 0 point and 3. We know that we're going to end up at plus infinity, and we know that we started at minus infinity, so it looks like this. What else do we have? We have an extreme value at 0, 0, and we have a minimum at 2 and minus 4, somewhere here. And we also have the point of inflection at 1, minus 2, somewhere there. So do I have enough information? Yes, I do have enough information. Look at this. The graph looks like this. And that's it. Okay. I mean, I erase it. So let's do it again. Seems to be better. Okay. Actually, no change of direction here. That one is better. Okay. All right. So this is how it works. Thanks for watching. And I'm going to do a few more investigations of those different functions with slightly more sophisticated domains and ranges and whatever in the next couple of videos. See you guys.